So I want to talk about two constructions of graphs, the Paley graphs and the countable random graph. They both appear in the same paper by Erdős and Rényi. This paper in 1963 has many beautiful things in it, but these two particular graphs or classes of graphs have proved to be very important since that paper. It turns out that there's a link between them. They don't just appear in the same paper, despite appearing totally different when you look at these two constructions. There is a link, and the link itself is rather surprising. It comes from algebraic geometry, namely work of André Weil when he was trying to prove the generalized Riemann hypothesis. So this is the paper I'm talking about. It's entitled Asymmetric Graphs. I'll explain that term in a moment. If you want some more on the background of Paley and the Paley graphs, here's a reference to a conference proceedings in which I give quite a lot of information about Paley and the history of his graphs. Of course, Paley did not construct the Paley graphs. If you look at the paper that's usually cited, there's nothing about graph theory in it. Paley was an analyst and an absolutely brilliant one, but he had no interest whatsoever in graph theory. For connections with the random graph, well, I've got a paper on the archive here. You can look at that. For more on the random graph, you should read several beautiful essays by Peter Cameron on this topic. So, so here are the details then. In this paper by Erdős and Rényi, they're interested in the question of whether a graph has a non-identity automorphism or not. So a graph is symmetric or asymmetric in these two cases. They're not really interested in the size or the shape of the automorphism group. They just want to know whether it's the identity group or not. And the first thing that they prove is this rather surprising result that while most finite graphs are asymmetric, most countably infinite graphs are symmetric. I'm using the words most here in a very vague sense, but in the paper they're much more precise about it. And as illustrations, they introduced these two classes of graphs. And the Paley graphs, this is a countably infinite sequence of finite graphs defined deterministically. The random graph, well, to be more precise, it's an uncountable family of countable graphs probabilistically defined. So these two constructions, on the face of it, they couldn't be more unlike than that. But nevertheless, there is a link between them. That's what I want to talk about. So first of all, the countable random graph. So you take a countably infinite vertex set, and for each distinct pair of vertices, you toss a fair coin to see whether they form an edge or a non-edge. In fact, you can have an unfair coin. The probability here could be anything strictly between 0 and 1, but let's be fair about it. They then showed that with probability 1, this graph has the following very simple property. Given any two disjoint finite sets of vertices, A and B, there is a vertex adjacent to all the vertices in A and none of those in B. So it's a very simple property, and I'd like you to remember that because I'm going to use it a couple of times. And they then showed that if you have any graph with this property, it is symmetric in the sense of having a non-identity automorphism. In fact, if you look at their construction of this, you can modify it very slightly to prove that any two graphs with this property are isomorphic. Even better than that, if you take any isomorphism between finite induced subgraphs, for instance, just one vertex in gamma mapped to one vertex in gamma prime, then you can extend that to an isomorphism between the two graphs. And in fact, it's not hard to see this. Suppose you've got an isomorphism between induced subgraphs. Well, number the vertices of gamma and gamma prime and take the least numbered vertex in gamma not in the domain of this partial isomorphism. By the universal property, by the property star of gamma and gamma prime, you can find a vertex in gamma prime not in the range of this isomorphism, which behaves in exactly the same way in the sense of having the right neighbors and non-neighbors. So you can extend this partial isomorphism by one element. And then you do the same, but in the reverse order. You come back from gamma prime to gamma. And by this back and forth argument, which is very well known in model theory, you can eventually extend the partial isomorphism to the whole pair of graphs, gamma and gamma prime. So up to isomorphism, you have just one graph, one countable graph satisfying this condition star. And that's the countable random graph, or simply the random graph. And this property of extending partial isomorphisms tells you that the automorphism group of this graph must be transitive on isomorphism classes of induced subgraphs. And that means it's very large. In fact, it's uncountable, and I'll give you a simple proof of that later. Now, does it exist? Well, yes, there are some very nice models of this. A year after their paper, Rado constructed what he called his universal graph. And the main property of this is that it contains every countable graph as an induced subgraph. And you can take the vertices to be the natural numbers, and two vertices, x and y, are adjacent if the smaller x appears, or rather 2 to the x appears when you write y in binary notation as a sum of powers. And it's a very easy exercise to prove property star. The model that I like best is based on quadratic reciprocity. You take V to be the set of primes congruent to 1 mod 4, that's infinite, and you define P and Q to be adjacent if and only if Q is a quadratic residue, that is a non-zero square mod P. And then the law of quadratic reciprocity tells you that this is a symmetric relation. So you get an undirected graph out of it. And a couple of well-known results in number theory, the Chinese remainder theorem and Dirichlet's theorem on primes in arithmetic progressions, give you the property star just in a couple of lines. By the way, if you take the other set of primes, those congruent to -1 mod 4, you get an anti-symmetric relation, and you get the random tournament where you decide which vertex beats which vertex by tossing a coin. Now, Erdős and Rainey were interested in the asymmetry of finite graphs, and what they proved was that most finite graphs are not just asymmetric, they're a long way from being symmetric. And they did it like this. For each possible order n of a finite graph, you've got 2 to the power n choose 2 possible graphs on a particular vertex set. So you can identify all of these graphs with their edge sets. So think of these, of the edge set as a subset of the set of all ordered unordered pairs. And then you can define the distance between 2 graphs on the same vertex set to be the order of the symmetric difference of their edge sets. If you like, that's the Hamming metric on the power set of V squared. It's the number of edge changes you need inserting or deleting an edge to convert one graph gamma to gamma prime. And then they defined the order of asymmetry of a graph to be the least distance of gamma from some symmetric graph. And what they proved that is that most graphs of order n have asymmetry close to n minus 1 over 2. More precisely, the probability as n goes to infinity that the asymmetry is greater than this fraction on the right is equal to 1. So most finite graphs are highly asymmetric. As an example of symmetric graphs, graphs that are highly symmetric, they constructed what we now call the Paley graphs. Paley wrote his paper in 1933, and in it he did some calculations which are very similar to those you need to prove that the Paley graphs are strongly regular graphs. The construction is you take the vertex set to be a finite field of order Q congruent to 1 mod 4, and you define the vertices to be adjacent if they differ by a quadratic residue. And you get an undirected graph because Q equals minus Q, and it's strongly regular with these well-known parameters here. And the calculation you need to do to determine lambda and mu is essentially what Paley did in his paper, where he was constructing orthogonal matrices. And these orthogonal matrices were needed to produce block designs for Todd, and Todd needed block designs in order to allow Coxeter to construct some interesting polytopes. And that's really where the Paley graphs came from. The automorphism group of a Paley graph, it's quite well known. It's this group of semi-affine transformations. We've seen these groups several times in this workshop. Okay. I was interested in trying to construct infinite analogues of the Paley graphs. And one way in which you can do this is by taking a union of finite fields. So if you have two finite fields of order Q and Q prime, there's an inclusion if and only if Q prime is a power Q to the E of Q. And when that happens, there's an obvious embedding between the Paley graphs. Now, if E is even, then every vertex in PQ, every element of the field of order Q has a square root in the extension field. So the induced subgraph of PQ is going to be the complete graph. And I don't want that to happen. So I'm only going to look at extensions where E is odd. And that means that the edges in PQ, rather PQ does not acquire any extra edges by being embedded in PQ prime. It's a full subgraph. It is its own induced subgraph. Now let's take an infinite set of odd integers. Make sure it's closed under taking divisors and least common multiples. Fix a prime P congruent to 1 mod 4, and then define f P to the capital E to be this infinite union of finite fields. It is a field because capital E is closed under least common multiples. So the sum, product, quotient, difference of any two elements is again in the field. It's locally finite, meaning that every finite set is contained in a finite subfield. It's easy to see that there are uncountably many sets capital E with this property, so you get uncountably many fields, and they're non-isomorphic because the finite subfields are just the fields that you started with in this union. So we're getting uncountably many non-isomorphic fields for each prime P. So You can then form the infinite Paley graph in the obvious way. Just take the union of the finite Paley graphs. And these finite Paley graphs are all induced subgraphs of it. At this point, I was very pleased. I had an uncountable family of interesting looking graphs. So I thought, let's try and do something with them. And then I realized that in fact, I only had one graph, because there's this theorem that each of these is isomorphic to the random graph. And this is the rather surprising connection between these two constructions in the Erdős-Rényi paper. So I want to outline the proof of this. I'm going to wave my hands just a little. I'm being a little bit careless about some details here, but this gives you the main points of the proof. So I showed you earlier that any countable graph with property star is isomorphic to R. So it's sufficient to prove that these Paley graphs have this property star. And I've repeated it again here. What we have to do is show that if you have two disjoint finite sets of vertices, you have to show that there's a vertex adjacent to all of those in A and none of those in B. So this set S of such vertices has to be non-empty. So let me define C to be the union of A and B. It's a finite set, so it's in some finite subfield. Now I want to introduce the quadratic residue character of this field. This takes the values 1 or -1 on the quadratic residues and the non-residues, and it takes the value 0 at the 0 element. And the point is that it's a homomorphism on the multiplicative group. It satisfies this homomorphism property. Now, for each element of the field not in this finite subset C, we have the following product. Let's just look at this product here. These chi's are equal to plus or minus 1. So each bracket is either 0 or it's equal to 2. So this bracket here, for instance, it's equal to 2 if chi of x minus a is 1, and that means that x and a are adjacent. Here, this bracket is equal to 2 if x and b are non-adjacent, so that chi is -1, and otherwise it's 0. So there are only two possible values for this product. If one of these factors is 0, then the whole product is 0. If they're all non-zero, they're all equal to 2, and there are n of them, where n is the order of C. So the value is 2 to the n. Okay, I've just repeated that there. Now, we want to find an x such that this expression here is non-zero, because that means that x is adjacent to all of the a's and to none of the b's. So all we have to do is show that there is an x for which this product is non-zero. So look at the sum of these products over all of the x's not in C, and it's sufficient to prove that that sum, little s, is positive. Because for every element x, the value is either 2 to the n or 0. So if this sum is going to be positive, at least one of the summands must be positive, and that gives us the x that we want. Right, let's imagine multiplying out this product here. Don't actually do it, just imagine doing it. You would have a product of 1's here and 1's here, and each summand would give you a 1. And the number of summands, well, it's the number of field elements not in C. The order of the field is q to the e. The order of C is n. So you're going to get q to the e minus n, 1's appearing when you multiply out this product and take the sum. The rest of the stuff, well, it's going to be a sum of products of values of chi. And the lovely thing is that we don't need to worry about it, because there's an estimate by Andre Weil for character sums, which implies that each of these products is not going to be too big. Specifically, he says that the product of all of these x minus a's and x minus b's is going to be big O of q to the e minus the e over 2, the square root of the order of the field as e goes to infinity. So S is going to be dominated by q to the e. You've got this constant n, and all the rest of the stuff here is big O of q to the e over 2. So as e goes to infinity, S becomes positive, and that's exactly what we want. We wanted to show that S is positive if E is large enough. And that means that one of these summands is positive, and that says that there's a vertex S that does exactly what we want. It's adjacent to all of the A's and to none of the B's. So there it is, that's proved. Let's go back and proved each infinite Paley graph is isomorphic to R. So although you've got uncountably many fields, you've only got one graph appearing, namely the random graph. As a corollary, you can prove that the automorphism group of the random graph is uncountable. That's well known, but the proof is not entirely obvious. But it is if you've got this isomorphism with the infinite Paley graphs, because the Galois group of this infinite field, well, the infinite field is a direct limit of finite subfields. And when you take Galois groups, direct limits become inverse limits. So you get the inverse limit of the Galois groups of these finite fields. The Galois group of a finite field is well known. It's simply a cyclic group. So you've got an inverse limit of finite cyclic groups. Well, when you take inverse limits of infinitely many non-trivial objects, you always get something uncountable. It's easy to see that this inverse limit is uncountable. In fact, there's an explanation down here using the Frobenius automorphisms, but it's just a basic fact about inverse limits. So this Galois group acts on the infinite Paley graphs. Therefore, by the isomorphism that I've just proved, it acts on the random graph, and it is uncountable. So the automorphism group of the countable random graph is uncountable. Earlier on, I mentioned that if you take powers, prime powers congruent to -1 mod 4, you get tournaments, and exactly the same sort of construction gives you an infinite Paley tournament. Just take a union of finite tournaments, and similar arguments tell you that although there are uncountably many isomorphic fields, the tournaments that you get are all isomorphic to the countable random tournament, the one where you decide matches by tossing a fair coin. So that's using the analog of property star. And there I've just given the basic model. Primes congruent to -1 mod 4 give you a model for this tournament. And that's it. Thank you very much for listening.
Thank you very much for giving such an interesting talk, Gareth. And are there any questions to speaker?
Can I ask a question?
Sure, please, Natalia.
Gareth, you have proved that this infinite Paley graph is isomorphic to R. Am I correct that you have proved that it's isomorphic to R with probability 1?
No, I've proved that it's isomorphic to R. If you take a countable graph, then with probability 1, it is isomorphic to R. I tell some of my colleagues in geometric group theory who study infinite Cayley graphs that they are studying a set of measure 0, because almost all countably infinite graphs are isomorphic to R. So what, if you like, what I have proved is that if you take a countably infinite graph, then with probability 1, it is isomorphic to one of the infinite Paley graphs. But there's only one countable random graph R. That's up to isomorphism. That graph is unique. But the probabilistic statement about it is that if you choose a vertex set at random, in the way I've described, then with probability 1, the resulting graph is isomorphic to R.
Okay.
Are there any other questions? Comments? Not at all. Let us thank Gareth again for such an interesting talk.